place. Okay, respect. So you learned it already. Okay, so I have some bad news for you guys. I'm not sure if this is a bad news for you guys, but at least it is bad news to me because today lecture ID is 10, and we have a total of 12 lectures. So we are left behind the schedule, which is a good news. So I might be able to use one extra week for you. So it may be possible that we're going to have a total of 13 weeks of lectures. But regardless of that, it's the fact that we are approaching the end of the course. And that's what makes me feel bad. Sad, not bad, sad. Because there's always this lecture time is the best time of the week for me. I don't know about you guys, but it's always entering big time. Saturday, Sunday evening, I already getting excited. Okay, finally I meet you guys. And this live conversation, I always missing that. Okay. Remember what happened a week ago? That was I made a recording about that. We scored 100% in in-class quiz. That was amazing. That was amazing because we scored 100% in a question that wasn't easy. It wasn't easy. So I don't know what's wrong with you guys. But I hope that we don't keep this way because you remember this promise about the dancing and everything. So my dancing session becomes to be overly lengthy if you're scoring 100% again, which I don't think because today we're going to ask something very complicated. But you're going to see that. Okay, so we will continue about the modeling of hydraulics. So already we know about this deal, about the land fluid theory. That's the first order differential equation that you can use to define the pressure at any given time. Extremely, extremely important equation. And that's something we're going to practice to use today a little bit. And then we're going to, if I'm going to write this equation, this first order differential equation, it goes like this. So it's a P dot is effective bulk modulus divided by volume size. And then the components that you're not so much familiar with at the moment, but soon you will, are flow rate in, flow rate out, and then there's this component that is a change of the volume. Now, today we're going to get started by looking at these components, which is a flow rates, flow types. So flow, in general, try to equalize the pressure difference. And pressure difference is the way that the flow will take place. Now we're going to learn what are the different flow types. And there are two different types. There are laminar flow and turbulent flow. And out of the two flow types, the turbulent is the most common and most important for us. And then once we're done with that, then we're going to take a look at the few components. In the hydraulics, there's a lot of different components available. And we're going to look some of the most often used ones. So we're going to focus on the throttle valve, which is a simple component. We're going to take a look at the direction valve. And in the direction valve, we can also take a look at something called digital hydraulics. I don't know if you guys have ever heard about term digital hydraulics. Have you? All right, so it's something that seems to be a big promise to field of hydraulics. Why is the case like that? That's simply because the problem in hydraulics, this is very much generally speaking, the problem in hydraulics is that energy efficiency is not so great because most of the time what we do in a hydraulics is that we put a lot of energy to the system because of the pump. So pump keep on producing the energy to the system, and every now and then we need the energy, but not continuously. And of course, there are some certain things that helps to prevent the use this extra energy, like load sensing pumps. But still, it's not so great solution to this big problem, which is losing the energy. All right, we producing excessive amount of energy to hydraulic circuit, and then we getting rid of the excess amount of energy by using different kind of valves. Valves are introducing pressure losses, energy losses in the same way. And this digital hydraulics is a promise that maybe instead of using these serious pressure differences and pressure drops, we could use something with a little less pressure drops. and it's based on a lot of on-off valves, poppet valves, which I'm going to explain you the concept. Because this is something that people are saying that finally there's something that is enhancing the hydraulics. Finally. Let me explain finally in a momentarily, but that's going to be the subject matter related to direction valves. Then the pressure relief valve is something that I'm going to leave you as a reading assignment. And then we're going to take a look at the cylinder and a pump. In a pump, we're going to take a look at the fixed volume pump, variable volume pumps, and load sensing pumps. How is that you can model them? And to make a model out of these components, you need to understand the operation principle as well. Okay, so that's what's going to happen today. Uh, so how that sounds? This was exactly what I was missing in a Sunday evening. This live discussion, argues, a lot of comments, questions. So, all right. So, like I said, not so much progress in hydraulics. Okay, that's extreme statement. Of course, there's quite a bit of changes in hydraulics. But now, if you take a look at the two machines here, these are two mobile machines. They are not same age. This, the one that is in left-hand side is roughly my age, 15 years old, 25 years old. This one here. Oh, sorry, this one here. No, more than that, more than a 50 years old. So he's my age. So he's a 50-something years old. So it's not the latest developments. But when you look at the construction design, and when you look at how the hydraulics is being used in that crane, and when you compare that to one that is really the recent state-of-the-art machine, the same operation or same way it needs to be used, there's not so much changes. There is still this lift cylinder. Yes, it is located in a slightly different ways, but still there is a 4-bar mechanism that connects the lift arm and swing arm, and that is connected by hydraulic cylinder. So roughly speaking, developments being not so great. Well, this is a little bit extreme statement, but when you step into cabin of these two tractors, you can see that, okay, there's a major difference. And the difference is this. This is how the gapping looked like 50-something years back. You see that at that time, the spools, which are the element, really the key element in the direction valve, were operated by manual sticks that are mechanically connected to spool. And the gapping look not so pleasant. And because always in the hydraulics, there's a great chance of different kind of leakages. You see that there is a little bit of oil in the floor and so on and so forth. And the ergonomics is not great at all. Whereas the new one looked like this. Now in the new one, the valves, direction valves, are not directly operated by a stick. I mean that there is no mechanical connection, but instead there is a joystick that sends the signal to direction valve, and that's the way you're controlling the machine. And ergonomics is in a different planet. So they look much better, and the usability, because of the ergonomics and other features, is significantly enhanced. That's how it looks. Okay. Still, the operation principle of the hydraulics is not being changed that much. But maybe this digital hydraulics will be the next big step. Maybe. It's been a promising field already quite a while, but we'll see. We'll see. So that's what I'm going to explain to you later today. All right. Then what is it we discussed a week ago? This is this first order differential equation that I explained in the first slide. And this is something that is extremely important for us. You must understand each of the components in the equation. And again, referring how it's going to be the written exam. By the way, note regarding the written exam, because some of you are worried about what's going to happen to you because you accidentally enrolled this written exam, which will be full exam. When that will be? Sometimes in December. 16th of December. Okay, now you would like to unroll yourself. I don't know if it is really needed or not. It may be a safe if you can somehow undo the enrollment. But for me, in my perspective, I couldn't care less. That makes no difference to my life because I'm hoping that each one of you guys will do the second midterm exam. And I'm hoping, begging, you're not going to go the full exam because the full exam is a classical paper exam. And I'm going to make it so complicated that you're going to cry when you see the exam paper. Why I would like to do it? Because when the paper comes back to me, I need to manually correct it. And I hate it. I hate it big time because I need to figure out from your handwriting what is it you wanted to say. And it's unpleasant, very unpleasant. So anyways, so now if you accidentally enroll to this full exam, you may ask from the student affairs office if this is a big deal or not. What did they mention in a student affairs office? You can cancel it by yourself. Yeah, okay. You don't, okay, so the problem is that you cannot enroll the midterm exam. Okay, here's the deal. So you will be all automatically enrolled because I'm expecting you to do it. So don't do anything. You of course will have this opportunity to do the midterm exam. So don't go and ask from the student affairs office how is that I can do the midterm exam because it's organized via Moodle. Okay, and the Moodle, if you have an access to Core's Moodle site, you will have an access to midterm exam as well. So no additional enrollment needed. So you don't need to do any second enrollment or anything like that. Quite opposite. Do nothing because you send an email for us, then we need to think about really, do you need to do some kind of extra enrollment? You don't. You simply don't. Okay, so that's about the practical business. Any other questions, comments regarding to that? I guess it is okay. Pretty clear. Pretty clear. Okay, so undo the enrollment to full exam and wait until we're gonna approach the midterm exam. Are we gonna do that right after we have covered everything? So there's gonna be, so let me take myself back here. Okay, so we need one more time for hydraulics and then real-time simulation games and then summary. So that's going to be 2 or 3 additional weeks. And then we're done. Okay, so back to this business. Okay, I was saying in terms of midterm exam. Question you can see in a midterm exam is that, okay, what are the different components in this differential equations? There is not a question asking you to derive this first order differential equation starting from the Big Bang. We are not expecting you to do anything like that, but we want you to understand kind of what is a physical interpretation of it and what it can describe and what it cannot describe. Okay, so it can describe the pressure and it can take a fluid flexibility into account because of the effective bulk models. It can take the volume size and changes in the volume size into account, and it can take the flow rate in and flow rate out into account. But it cannot take into account the pressure waves. Pressure waves sometimes takes a place in the long pipelines. Not so much about the hose lines, but the pipelines where there's a very lengthy pipeline. You keep on pressurizing it, and you suddenly closing the pipe. You close the pipe, you close it here as well, so it's possible that there is a pressure wave that is traveling back and forth between these two blocks. That needs very fast hydraulics, and not typical problem in the mobile hydraulics. It can be the case in certain industrial application, but not very common one. You can, of course, take this into account as well by modeling the pipeline by using a number of different volumes and totals between the volumes. But that's not usual practice because this can easily lead to problems in a simulation. And the problem would be that if you keep on decreasing the volume size, look at where the volume is located. So the bulk modulus divided by volume. Now, if this volume becomes to be very small, number-wise, numbers will go very high. And that's going to be something that is called numerically stiff system. Numerically stiff system, shortly speaking, is a system where you have a frequency in a very, very wide band of frequencies. So there is a low frequencies and high frequencies. This combination is very nasty for numerical integrators because they can tune themselves to deal with the high frequencies and they can tune themselves to deal with the low frequencies. But if this combination is typically quite of the problem and you want to avoid it as much as you can. Okay, so that's it. That's about this differential equation. We also learned about how is that can be used in the case of a simple damper. In a damper, here is your first differential equation and your second differential equation, and now the flow rate try to equalize the pressure difference. This is a little bit of chicken egg situation. Which comes first, pressure difference or the flow rate? That doesn't really matter because they will happen simultaneously in a simulation. But as soon as the pressure here started to change, these two pressures started to change, the volume, the flow rate tried to equalize the pressure difference. That's how it roughly happens. But on the other hand, if you suddenly make the flow to happen, the pressure difference will take place as well. So that's this chicken egg situation. Okay, and we learned that in real hydraulic circuits, there's something that is called discretization procedure. And in discretization procedure, you're dividing your hydraulic circuit within the volume where you are assuming pressure to be equally distributed. Equally distributed means exactly that we cannot take these pressure waves into account. What that means? It means that I can make an assumption that the pressure right after the throttle here will be roughly same than the pressure close to the piston. And it's the case if there is nothing that introduces the pressure losses. Now, there is nothing that introduces the pressure losses the way this system is described. So this assumption is valid. Okay, makes sense. What? So you do this. Okay, so please do it then. Because I'm not sure, because the way I see is like empty eyes. I see nothing. No lights from your eyes. Okay, so yes, okay. And what else? Can-do attitude. Okay. All right, here's an example. So now I have a system here which is a hydraulic cylinder, and the flow rates enter the cylinder. So what's going to happen to it? So the flow rate, which is noted here as a Q, came into this system. How is that I can compute the pressure at any given time using this first order differential equation? Okay, again, certain steps we need to take. First step is that we need to define the equation that tells what is the volume size. The volume size will be, the hose volume, this one here, where the flow enters the cylinder. That's VH divided by VH, then multiplied by the cross-section of the piston. This is a cross-section of the piston, multiplied by the stroke, whatever is the piston location at any given time. That is measured by X. X coordinate started here. Farther off, the further off the cylinder is, the piston is, more is the volume size. That's how it works. So that's your first equation you need. Okay? Second one is effective bulk modulus. Effective bulk modulus, now the components that I have is oil, which is accounted by using this guy here. Then I have the bulk, the flexibility of the hose, that guy here, and the flexibility of the cylinder. Each of them are with the corresponding the volume size. Okay? And when I compute the effective bulk modulus out of that equation, that's how it reads. And the final equation is the volume change as a function of time. Okay, that's going to be then cross section, which is the same than we described earlier, and then it's going to be x dot, which is what? Velocity. Velocity. That's going to be your flow rate. So it's going to be cross section multiplied by corresponding velocity. That's going to be your flow rate, which is kind of leaving from the system. That's why when you enter the things in your differential equation, this guy must be minus in a size. Because think about the positive motion. So the volume will get bigger. So it's kind of sucking the flow rate out of the system. So the pressure will drop. All right. Then the final component, which is this Q, which is entering the system. Because it's entering the system, that have to be plus in a sign. And whatever you make this kind of manual hydraulic modeling, make sure you have a drawing some kind that you are not getting confused about the signs, about the minus and pluses, because that is a typical mistake that I can see in a hydraulic modeling. Make a drawing to yourself. You see that the volume comes in or it leaves. If it comes in, that's plus. If it leaves, that's minus. So it's simple like that. But how you initially defining things, that is up to you. But only thing you need to do is to be consistent. And the only way you can be consistent is that you make a drawing to yourself. All right, so have you guys seen this YouTube video about the worst professor ever? You know, I was making the presentation for this week, Wednesday, and I was watching that one more time because it's so good. You know, the worst professor ever is keep on telling about make a drawing, make a drawing. And I see that I am kind of like that guy too, because I keep on telling, make a drawing, make a drawing. So make a drawing. And take a look at this worst professor ever from YouTube. So none of you have ever seen it, or have you seen? No, you haven't. Okay, go to YouTube and type worst professor ever, and it's not me, but it's somebody else. It may be me too, because there's a long list of professors that are not scoring so well. I mean, that they are not teaching so well. So you may check that if you want. Okay. All right. This is something that is related to the flexibility of or compressibility of a fluid. Assignment, related to assignment. Maybe this is coming a little bit late, but I wanted to explain you how is it you can compare the natural frequency of the situation as described here in this figure. And what I have in the figure is that I have here a hydraulic cylinder, which is a two-way hydraulic cylinder, so you can pressurize the piston side and piston rod side. So it can be pressurized both sides of the piston. Okay. Then I have here a mass that is located top of the system, and mass is denoted as an M here. And I'm asking, what is the natural frequency of the system? And the natural frequency, you do know that it can be computed when you know the stiffness and the mass. So it's all the time relation between the stiffness and the mass, and more specifically is a square root of the stiffness and the mass. Okay. So square root of the stiffness and the mass, ratio of stiffness and of the mass, to be more specific. So the mass goes directly here. And the only component you need to define is stiffness. Okay, stiffness in turn is all about how is a relation between the change of the force and the displacement. That's what it is by the definition. Okay. Now, change of the force. If you think about how to produce the force in this case, the force will be such that it's going to be this cross section area, which is cross section 2 multiplied by corresponding pressure 2 minus pressure A1 multiplied by corresponding cross section area. That's how you can compute the force if ignoring the friction, which we're going to do this time. Okay, now if you're going to change what out of these four components can change, it's going to be pressure only, because the cross section cannot change at all. It's a constant component. Now here it is. That's how it can be defined. And then the change of the difference, the displacement correspondingly can be computed as it is shown here. Now here's your displacement, here's your force difference. This is how the K can be computed. And now if you use a definition of bulk modulus, sorry that I'm a little bit fast here. Using the definition of bulk modulus, you can use and this relation which can be seen as well, this came from the definition of, this is by the way the definition of bulk modulus, sorry about that. So it came from this equation, and this came from the previous slide. The stiffness can be computed as it is shown here. And this will be your way to compute the natural frequency of the system that consists of the mass and two-way hydraulic cylinder. How that sounds? Makes sense. How you do it then? By substituting. Substituting the right component in the right place. That's pretty much all you need to do. The most problematic component is, of course, this guy, effective bulk modulus. But other than that, fairly straightforward. Makes sense. Okay. So moving on then. So let's look at the one thing that I was unable to cover a week ago, and that is these flow types. And then we're going to move on to different components. Now the flow types, as I mentioned in my introduction today, we have two different flow types, laminar flow and the turbulent flow. Laminar flow is something that the viscosity plays a role. And that takes a place, well, roughly speaking, this is very generally speaking, laminar flow takes a place when the pressure difference is small. Okay, this is untechnical term, when the pressure difference is small. How small it needs to be? Well, roughly speaking, if it is less than 2 bars, then there's a chance that the flow type is a laminar flow. And now, in a modeling perspective, there's a major difference between the laminar flow and the turbulent flow. And it's all related to how is a pressure difference versus the flow rate. So, scenario is this. Here's my pipe. And I have here some kind of a throttle, something that introduces the pressure losses. Okay? And I have here P1 and P2. And I'm assuming that P1 is bigger than a P2. So the flow will travel from left to right. So the pressure difference that I keep on telling is, of course, P1 minus P2. P1 is assumed to be bigger, so this is going to be a positive value. So the pressure difference is a positive value. Now the flow that enters through this throttle, that's going to be a function of the pressure difference. And it can be function of the pressure difference in two different ways. It can be either be linearly related to pressure difference. Let's tell that there is a parameter CV multiplied by pressure difference. This time of the flow will be a laminar flow. This CV here depends on the application, and I'm going to show you pre-calculated tables to take this CV into account. But in a modeling perspective, the more important and more interesting is this, that the flow rate and the pressure difference are linearly related. That means, by the way, that if you look at the laminar flow in a particle, we came back to the particle, and you're going to see something surprising, which is a rotational particle. Not rotational particle, but there's going to be whirling of the particle. It looks like a rotation. All right, so if we're going to take a look at the particles, how they will go through this throttle in case of laminar flow. In a laminar flow, they will go with a good order. So they will go smoothly, like way they kind of travel like this. So there is no disagreement. So they all go with a good agreement. So they roughly are not changing their road too much, but they're getting closer to each other, and then they're getting far away from each other. So that's going to be the laminar flow. Another type of the flow is this turbulent flow, which is more common and takes the place when the pressure difference, this one here, becomes to be bigger, more than a 2 bars. Well, in a mobile hydraulics, it's very common that the pressure differences are more than a 50 bars, 100 bars. They can be easily 100 bars. So it's clear that in those cases, is all the time a turbulent flow. In turbulent flow, the particles are traveling with disagreement. I mean, with the whirling. So if I'm going to take a look at the particle here, so when it enters to this throttle, so it's going to whirl like this. So it's going to be behaving like this. It's almost like a rotation of the particle, which is, of course, not the case, but it can whirl like this, and that's called turbulent flow. Modeling-wise, what's the deal with the turbulent flow? Well, in a turbulent flow rate and the pressure difference are quadratically related. So there is let's put it here again, the parameter. So this relation is a quadratic relation. You can put it this other way around. So the pressure difference and the flow rate, the flow rate is a power 2. So that's how it is. Okay, so these are the two flow types. And for us, way more significant is this turbulent flow. And that's what we're going to take a closer look when we are looking at the different components. Okay, so that's about it. And then how are you defining what is what? Theoretically, there's a way to do it, and it's called Reynolds number. I'm sure you are familiar with this. And the Reynolds number is telling you, okay, when flow will convert it from laminar to turbulent. And of course, it's not going to be the one single moment that has happened like that. But there's a period of time that is unclear. Not period of time, but period of pressure differences that is unclear what it is. So it can be a mixture of laminar and turbulent. But roughly speaking, you can define what is what by comparing something that is called Reynolds number and compare that against something that is called a critical Reynolds number. A critical Reynolds number is something you can find from pre-calculated tables. If your number is less than a critical Reynolds number, then you can make a safe assumption that your flow type is laminar, meaning that in a modeling wise, you can use this relation delta P in your modeling. That's how it's going to go. And again, this is, if you look at the flow rate and pressure difference, that means that this one is behaving linearly. And this angle here is defined by this one single parameter. Now, if the number is more than a critical Reynolds number, then it's assumed that they behaves quadratically. So this curve here is a square root curve like this. So roughly that's how it behaves. Okay, so that's for your information. Now, this is what I pretty much explained already. So this is how the flow rate and pressure difference are related in the case of laminar flow. And again, keep in mind that there is this one single parameter, which is this angle of the curve that relates these two matters. How you compute it? Well, here is an example about the pre-calculated tables. You see that, if you have rectangular cross-section, throttle, which is a rectangular cross-section. I don't know how you can do that, how you can manufacture something like that. Unclear to me. But anyway, so there's a flow entering here and leaving here. In a case like this, take a look at this. So flow rate and pressure difference are linearly related. How this angle is defined by once you know the B and H. And let me see, the H is, I'm sorry. This is H and this is B. Once you know the geometry of the throttle, and the L is the length here. And look at this. This is a kinematic viscosity. Viscosity is involved as well, as I explained a week ago, I think. So that's the case. Here is a little different kind of throttle, which is very commonly used. So this is drilling. So once you know the diameter of the drilling and the length of the drilling, that's all you need to know. And the viscosity is needed as well. And then more and more examples. So there are pre-calculated tables to compute that missing parameter. Makes sense? Okay, then the final, this turbulent flow, where from our perspective, the important information is this. Flow rate and the pressure difference are quadratically related. So meaning that if you see the curve like this, which is nonlinear and acting quadratically, that's going to be the turbulent type of the flow. This type of the flow, if you see it, you can model as a laminar flow. Makes sense? All right, I have a question to you. Is this everything that I have explained so far today, is this too easy? So you knew it already a million years back. You knew it already a million years back. Pretty much so. Are you getting bored? Pretty much so. Yes, sir. Uh, so is that so? Can you please again ask me again? Oh, yep. Oh my God. What do you guys say? Is that a worth of coffee coupons? I owe you quite a much. I owe you a coffee coupon, and now you, then the rest of you, I owe you a Dan. So I have a lot of debts already. Awesome question. Yes, it will affect. It will affect. How it will affect? That's going to be very complicated to compute. And that leads us to next topic, which is the modeling of different components. In theory, yes, it is possible to take these dimensions into account, take these loss components and parameters into account, but at the end of the day, it becomes to be overly complicated. And we're not going to do this way, but we're going to instead using something that is available for us. And something that is available for us is information offered by manufacturers' catalogs. Because manufacturers, hydraulic components manufacturers, they will offer each of their components, they will offer something that is called characteristic curves, defining the characteristics of their components. This is information that allows us to define these otherwise complicated parameters like dimensions. So we will use a shortcut. And that's method is called something which is called semi-empirical modeling method. Okay, how many of you knows Professor Heikki Handros? You know him. Okay, he is one of the inventors of this semi-empirical modeling method. He made these papers about the semi-empirical modeling method already 1992, 30 years ago, so quite a while ago. But he is one of the founding members of this entire modeling procedure. That's going to be something that I will explain you next, how it sounds. So again, when you see next time you see Professor Handros, make sure you salute him because of his accomplishment regarding the semi-empirical modeling approach. Deal. Don't do it because then he's going to ask like, what is wrong with you? So who asked you to do it? He's not going to be happy to me. Okay, so here are the different components then. Okay, so the first one is a throttle valve. Okay, this takes back to your question. How you can model it. So because throttle is already a component that you need to know the dimensions. And it becomes to be overly complicated, more complicated when you look at the other components like direction valve. Direction valve is already something that there is a throttle size that is changing all the time, continuously. Because the way the direction valves are operating, there's a spool that is plugging the flow, sometimes plugging a little bit of flow, sometimes not plugging at all. So how you take that into account? And within 10 minutes or so, there's going to be first-in-class quiz of the day. Ready for that? Okay, so the first one is a throttle valve. All right, so this throttle valve is a good example about the semi-empirical modeling approach. Well, Before we step into that, what are the modeling possibilities we have? Well, of course, we can use analytical approaches to model this component. That would mean that we need to use all the parameters you can find in real life, meaning that in the case of, just to give you an example, the pressure relief valve, you need to first create the equation that defines where the spool or the poppet of the pressure relief valve is located at. And based on that information, you can compute the orifice size or the throttle size, its physical dimension. But that you need to know information about how is the mass of the poppet, how is a spring coefficient, and so many other parameters that are, end of the day, extremely difficult to get. So that's analytical approach is not practical. Alternative approach to you would be to use a lot of measurements. To take the component, carry out, conduct awful lot of experiments, measurements, and describe your component using a kind of the black box method. This is very common in the current world because at the moment there's data-driven models. Data-driven models meaning that there's a lot of data behind the model, so there is nothing else except the data. And you can get the data from the measurements or very advanced simulation, typically from the measurements. Now in these other alternatives, we can conduct a lot of experiments. We can store this measured data to black box kind of the method, which could be a lookup table or something that tells if this happens, then the flow rate will be this much. This is going to be called empirical approach. Accurate, but needs a lot of measurements. And we don't want to do measurements because we love computer simulation. So this, what Professor Andrews figured out, is somewhere between these analytical approaches and empirical approaches. And that's why it is surprisingly called semi-empirical approach. And semi meaning that yes, we're going to get started from the analytical equations. And these analytical equations will be after mathematical manipulation expressed in a way that all the unknown parameters can be obtained from simple measurements, which is already offered by manufacturer's catalog. So we actually do need to carry out no experiments whatsoever, but we can open the catalog, we can look what are the characteristics. That's it. Here's an example. Okay, this is this throttle valve. The throttle valve empirical model needs to know, or to do it, you need to know the following information. So you need to know about something that is called discharge coefficient. All right, this is going to be our first big problem because discharge coefficient, you need to use a lot of pre-calculated tables, or you need to do a very advanced flow analysis to figure that out. Not so tempting to figure that out. Then the next component you need to know is a diameter of the throttle. This one here, diameter. Sounds easy, but a little difficult to do in a practice because the throttle valves will be somewhere inside of the component. So even knowing that could be a big headache. It could be a big headache. And then you need to know the pressure difference, of course. So this, what is under the screw root will be the delta P, and then the density and so on and so forth. That's another thing you need to know. Now, I'm going to express this equation by using one single parameter, which is called CV, and that's going to be my semi-empirical parameter. The CV will be equal than the one that is shown here. So I'm losing no accuracy whatsoever, because if you substitute this one here back to the here, is all the time same, no difference. But why I wanted to do it? I wanted to do it because manufacturers, they're offering curves like this, which is called characteristic curves. And in that curve, I can define this parameter CV. That's all I need to do, and then my model is ready. Make sense? Makes sense. Okay, guys, I would like to let you go to have a break, but I don't gonna do it that today because if I say okay, 5 minutes break, it's gonna take you 20 minutes at least, sometimes more, before you come back. So I lose you. I don't trust you guys anymore because I don't want to run after you and say in a cafeteria and say, hey, come back, come back. I wanted to have, I still have some couple stories that I would like to tell you. So what should I do? Or should I trust you? I'm suspicious. I'm suspicious. So you have this can-do attitude and respect. That you respect me. So if I allow you to go to break, you will be back in 5 minutes. 5 minutes because I need to leave. Let's say that I need to leave at latest at 5:50. I'm watching you. Please come back in 5 minutes. All right. So 5 minutes break.
In digital hydraulics, the system variables, pressure and flow, are controlled with multiple on-off directional seat valves. Each valve is solenoid operated and has only two possible positions, on and off. This is why the term digital is used. These valves are used to implement all valve functions, such as pressure, flow, and directional control. Contrary to a traditional hydraulic system, which has many different types of valves, a digital hydraulic system has a large number of only on-off valves. By connecting in parallel three on-off valves of different sizes, such In digital hydraulics, the system variables, pressure and flow, are controlled with multiple on-off directional seat valves. Each valve is solenoid operated and has only two possible positions, on and off. This is why the term digital is used. These valves are used to implement all valve functions, such as pressure, flow, and directional control. Contrary to a traditional hydraulic system, which has many different types of valves, a digital hydraulic system has a large number of only on-off valves. By connecting in parallel 3 on-off valves of different sizes, such as 1, 2, and 4, 7 different flow quantities can be achieved. 5 on-off valves can achieve the control resolution of a traditional proportional valve. A group of on-off valves in parallel make up a digital flow control unit, called DFCU. At least 4 of these units are needed to substitute a proportional valve in a hydraulic circuit. Each DFCU is used to control one of the 4 control edges. The main benefit of digital hydraulics is the ability to control each control edge independently. This reduces power loss and enables precise control. Additionally, seat valves have zero leakage, as opposed to the In digital hydraulics, the system variables, pressure and flow, are controlled with multiple on-off directional seat valves. Each valve is solenoid operated and has only two possible positions, on and off. This is why the term digital is used. These valves are used to implement all valves.
Hey, I'm very proud of you. So you came back timely. You put the timer. Very nice. Okay, so I think we developed the trust relation. So next time I can allow you to go again. But hey, I have a question because one online participant is asking whether or not there is a student-specific initial values available. So are those available in a Moodle database or are they not? How is it? Hey guys, can I have your attention, please? Hey guys, how is it? Do you know if you already can find your student-specific initial values in Moodle regarding their simulation work? Are those available or they are not available yet? Yeah, well, because each of the students, you have your own parameters to model the system we're asking you to model. So have you found those or not yet? Not yet. Okay, so my answer to online participant is that we need to figure that out. I need to ask from Suraj. So you do not know how to get your student-specific values. Hey, so correct, correct. It's not mentioned. No, there is a table that tells you what kind of numbers you should find. Because if we can allow you to figure it by yourself, this team, which is what is the name of the team again? What is the name of your team? Okay, so A team. So A team, you can all use the same initial values. And that's not going to be good because you're going to do a teamwork like no limit. And that's why we're going to want to give you a different kind of initial values. But how to find these initial values, I need to check that. I need to double check that. Okay. Hey, another note. This is a short note too. You know, the simulation assignment, there are two steps. And I don't know how to put it because you guys are going to be angry when you're going to hear the second step. The first step is that you need to do the assignment by yourself. And then you need to create the other work. We are using your brains to do the peer reviewing. So we would like you to check. You can submit your work, and then you will get the couple work that are made by your fellow students. You need to give them a grade. So it's called peer reviewing system. And I know that some of you hate this peer reviewing big time, but it's going to be part of the game. You will get the instructions how to do the review. How do you creating your fellow student work, and you just follow the instructions. Okay. So we are not going to create it, but you will. How that sounds? So it sounds great. So you're going to score very high. Well, that's what you're going to say today, but when you're going to see the rules, you will be less enthusiastic. I think. I don't know. I think. Okay. So I was here. So we were in this throttle valve, and here's an example. So this is a characteristic curve. How come I lost it? Okay, so it's back. All right, so it's back. So this is a characteristic curve that is offered by a manufacturer. And what I have in this characteristic curve is a flow rate. And look at the units that I'm using. So I'm using the liters per minute, which is a typical way units is being used in hydraulics. But when I wanted to create the model, I want to use SI units as much as I want because converting units in a hydraulic modeling is a big headache and not recommended to do it. So try to avoid it as much as you can. Okay, so that's going to be my flow rate. As a pressure difference is this one here. As a pressure difference is offered as a bars. Bars, another big headache, but this is how you typically see the units to be used. But again, it's extremely important that you're converting everything to be in SI units. Okay, my pressure difference is here. My flow rate is here. This is my characteristic curve. First thing that I can learn from the characteristic curve is that this particular component is having a turbulent flow. How I know that? Because of the quadratic nature of the curve. So it's not linear, but quadratic. Okay. So now if that's the case, it doesn't matter where I'm going to take the point out of the curve, so I can take the point anywhere I want. I substitute the information to this equation, which is defining this semi-empirical parameter CV. Okay? So I'm taking the point out of this 30 liters per minute, and in that case, the pressure difference is 100 bars. So this is when I converted 100 bars to be in SI units, in bars, no, in megapascals, so it's a pascals, and then this 30 liters per minute is converted to be SI units as well. And when I do the math, this is how it looks. Take a look how bad is the units. So you don't want to convert the units because they are so bad. Anyways, so my model is almost ready, so I have my unknown parameter. Only thing is that I need to make this a final equation, which is shown here. So my flow rate through this component will be my semi-empirical parameter multiplied by pressure difference. But because the pressure difference might have a minus sign, I need to use a minor trick here. This one here which is under the screw root, I'm going to use an apps there. So I will make sure that whatever goes under the screw root must be positive in the sign. But because the flow can go left to right and right to left, I need to take that into account. And I will take that into account by using a sign component, which is this one here. Sign component gives you 1 or -1, depending what is it you have here inside of the parenthesis. So if something you have in a parenthesis having a negative value, sign will give you -1. If it is positive, it's going to be 1. If it is equal to 0, it's going to be 1. That's going to be your equation. End of the story. How that sounds? That's called semi-empirical modeling approach. Pretty straightforward. Right. Okay, let's take a look at another component. Direction valve. You know, there's a many different type of the valves. And we're going to take a look at the valve today that is actuated by using a magnet. But it necessarily need to be the case. Remember, we looked at valves in the very beginning, and where these were mechanically operated. There was a stick connected to a spool, and the spool is the one that is moving inside of the direction valve. And now comes something extremely important, what is related to valve modeling, because valves consist of moving component. So in the first step of the modeling of the valves is that you need to know where this moving component is located at. And again, you could model that by using equation of motion. But that becomes to be complicated because then you need to know all these tiny parameters about the masses and springs and so on and so forth. And it's not recommended to do it this way. But you have to have some kind of equation that tells where the spool is located with respect to the valve itself. That's going to be the first step. And once you know the valve position, then you can compute the flow rate to the valve. So 2 steps needed. And here it is, put it in writing. So here's an example. So this, what you can see here in the right side of the slide, this is a pressure relief valve. And the pressure relief valve is typically closed. And it is closed because the pretension of the spring here. So there's a spring that makes sure that the valve is closing this cap fully. Okay? What then happens is that this spool is pressurized here, but the same amount of forces are created the opposite direction because the way that it is constructed. So it will remain closed no matter how is the pressure inside of it. But then we have this kind of secret tunnel. Secret tunnel is this one here. So there's a throttle valve that reduces the pressure, takes the pressure this side of the spool, because of this pressure, when the pressure becomes to be higher than pretension of the spring here, it opens. But again, how much it opens at any given time, the one possibility to model it would be to take the spring coefficient into account, pretension into account, mass of the spool into account, friction into account, and all that becomes to be too complicated. So we don't want to go that way. So we want to use a shortcut to model the spool position. But once we know the spool position, then we can compute the flow rate, which goes through this corner here. But again, flow rate or the flow dimension where the flow can go through is a function of the spool position. You see that clearly, right? Okay, makes sense. So how we can do that in the case of direction valve? Well, before we look at that, let me just give you a little bit of vocabulary, a little bit about what are the things that you need to know. How the direction valve operates is because of this moving spool. So there is a spool that goes left and right in this, like you can see in this picture here, and there is a land. The land, which is this thicker part of the spool, that blocks the direction of the flow. or that blocks the axis of the flow. And the drawing symbol of this valve look like this. So it connects the ports A and B by pressure and the tank. And how it do it that, you see that if there's a pressure line here, if you move this stick to the left, it opens the line between A and the P. And when you move this stick to the right, it connects the pressure and the B, which is this operation condition. And when it is in the middle, then it is assuming that no flow rate whatsoever. You see that there are three different scenarios: P to A, P to P, or no flow whatsoever. So to make sure which scenarios you need to use, you need to know the spool position. Makes sense. But not just that, but you need to know the details of the spool position, because this throttle size will vary as it is a case of pressure relief valve. So it's not necessary in a fully open, but it can be somewhere fully closed and fully opening, anywhere it wants actually, because this sticks. You can put it anywhere you want. So it's not necessarily fully closed or fully open, but in the middle, 1/4 of it, 1/5 of it, anything is possible. Okay, so that's what it is. Now, here's another cross section of the direction valve. Now, in this case, I have here pressure line, which is here in the middle. And then again, there's a spool. So this one component, this component is a spool. This is a land. You see that this is something that is called zero land, because it just barely blocks the connection when it is in the middle. Sometimes the land could be smaller than this blocking. So it's possible that even in the middle condition, there's a flow rate that travels between the different possibilities. That's one scenario. But here it's just blocking it. And understand that if I'm moving this in left, then it's going to open this channel here. So the P and A will be connected. And if you're moving that to the right, then this will be opened. So that's the way that it will be. Not that, but this will be opened. So that's the way it works. So what is, by the way, the drawing symbol for the direction valve as shown in the picture? This is not in-class quiz, but soon there will be an in-class quiz. Is it going to be A, B, or C? You can be relaxed. This is not going to make your life any different, because this is not the in-class quiz. But which one is correct? Okay, so team A is voting. Is it the entire team is voting this one, B? Okay, what about Team Finland? No comments. Okay, no comments from Team Finland. Okay, what about what are the other teams we have here? No other teams. Other teams too, no comments. So we only have one team that is voting B. Okay, other teams, do you agree that Team A, or you don't like it? It is B. It is B. Because this connection is missing, because it's a zero land system. So that's how it is. Okay, these are the different scenarios. So this is where the land is smaller than these drillings. So its middle position is this. This is this is what we just looked at. This is where the land is a little bit bigger than the drillings, and it's going to be still the same drawing symbols. Okay, but then comes something extremely important. The valves can be constructed differently depending how is the flow rate to the valve and valve opening. Many scenarios, and in this class we can assume that this relation is linear. And we also assuming that we are dealing with the zero land valves, meaning that as soon as we're moving the spool to be left and right, there is immediate flow. But that's not necessarily the case, because if there is a positive land spool like this, you need to move your system quite a bit about left and right before you see any flow whatsoever. You understand that? Because you need to get rid of this overlapping. And you can get rid of the overlapping when you're moving this much to the left and right. But then there's a very much used at top of the valve, which is a proportional valve. That means that the valve opening and the flow rate are not linear, but nonlinear. This scenario could be like the one that is shown here. This is used quite a bit in certain applications where you need to use a lot of velocities, like in a crane. Sometimes you need to use a full speed, and sometimes you need to use a lot of accuracy. Okay? So when you use a full opening, you have full speed. You have a lot of speed. Whereas when you're coming to be close at this position, you can get a lot of precision. You can get a lot of accuracy to make sure that you're exactly positioning your system where you wanted that to be. So that's proportional valve. Okay, now that is modeling business then. Okay, like I say, 2 steps to take. The first step is this. And now, please put your full attention to me, because I'm going to ask momentarily what this equation is describing. Okay, let me explain that to you first, and then I will ask. Okay? So you all with me? Everyone? Yes? Yes? Yes! Okay. Now we are assuming that we have a valve, direction valve, which is shown here. So it's closed in a middle position. This is drawing symbols. And then I have here magnets. And assuming that there is a magnets that are moving the spool back and forth. Very typical scenario, because remember in my first slide, I saw that tractor with these joysticks. So what the joysticks are doing, they're sending signal to direction valve. And then there is a kind of amplifier, which is a magnets that are moving the spool according to the joystick position. Not immediately with this, but with a certain delay. The delay is not significant, so it's almost non-existent, but still, you're moving your joystick to this direction. What happens mechanically is that, there's a signal that leaves from your joystick to the direction valve, and the spool is moving accordingly. How much it is moving? That is defined by this first order differential equation, which is a delay equation. This equation describes the spool position. How it describes that is by first order differential equation. So I have a signal which comes from the joystick. So this is a operator or automated systems that are controlling your devices. And then I have here spool position, previous step of the spool position, and then something that is called time delay. Because it's theoretically possible that the signal that you're sending in, this one here, as a function of time could be like this. This is time. So you're sending a signal where the signal jumps from fully closed to fully opening like that. So there's a step. Now the spool cannot do the step because spool having the certain inertia. And also the forces that are made by these magnets are not infinite, but there are with a certain limitation. And that's why the spool will follow the signal, the step signal with a certain delay. And how big is a delay is defined by this tau here. So now the real position of the spool will be like this. And this time here is defined by tau. You can get it from the manufacturer's catalog. But my question is that what is this equation describing? Do you guys know what it is? What it is describing? Spool position. Spool position. And once you know the spool position, then you can compute the flow rate through the valve. Spool position. Yeah. Spool position. Okay. All right. So where you can get this time delay then? Where you can get it? Now you can get it from from the manufacturer's catalog, because manufacturers are offering the information about how fast is the valve. And it's made by an experiment where you're sending a signal to spool, and the signal is this kind of a sine signal where you start increasing the frequency. So it's a fully closed, fully open signal to the valve, and you're increasing the frequency until it is like very high frequency. At a certain point, spool cannot follow this anymore. So it's left behind because it cannot move as fast as the signal itself. And when it's left behind enough, that's when it is defined that, okay, that's going to be your speed of the valve. And it comes from, this is what is called body diagram. I'm going to show you an example momentarily. And when it is left behind something that the value is of minus 45 degrees, that's your speed of the valve. But again, this is offered by manufacturer's catalog. Example will come momentarily. Okay, makes sense. All right, then once you know the spool position, then the final thing to do is to model the flow rate, and we're going to use this semi-empirical model where the spool position is multiplied by CV. CV you can get directly from the manufacturer's catalog. End of the story. So it's simple like this. First, spool position by using this delay equation with this tau that is coming from the body diagram. And once you know the spool position, then you can compute the flow rate to the valve. And again, you need to know the pressure difference that is coming from other sources. But that's it. Pretty straightforward. Makes sense? Makes sense. Okay. Okay. How is the success rate then? So physical interpretation of equation below. Pressure drop due to a valve. Flow through a valve. Spool position. Number of boards in a valve. You think so? You make me feel scary. You really think so? Okay, no, I don't think so, because if I'm going to take a look at the online participants, they're voting like 15%. No, it's my classes. Oh, they say 98%, 99%, 100%. Dance power 2, whatever that might mean. And then 100%. All right. So then what I will do is that I will continue, and I will get back to this momentarily. Is that okay? Okay, how much time I have? So I have at least 15 minutes. Okay. Okay, these are the different scenarios. This is how the direction valve is connecting different ports. So the scenarios is, this is what we already learned. How are the scenarios? So let me practice this. So let me take an example from the manufacturer's catalog, and let me create the model for you. Okay? So, and let me then get back to this digital hydraulics, because at first I want to show this example. Example, model direct direction valve. A manufacturer gives the properties of the proportional valve according to the picture below. So here's the first picture. So it's telling the valve opening and the flow rate. You see that this is a zero land valve, because as soon as you move the spool to left or right, flow started to go through the valve. So zero land. And you can also see that this relation between the valve opening and the flow rate is roughly linear. Not exactly linear, but linear enough that it can be modeled as a linear way. And then it's mentioned by manufacturer's catalog that nominal flow with the full opening, meaning that this point here is 25 4 liters per minute when the pressure difference is 35 bars. All right, here's an information that I need to compute my semi-empirical parameter. So I'm going to take these 25 liters, I'm going to convert that to be in SI units. I'm going to take my fully opening. Here is a 10 volts. I'm going to put that there. And then I'm going to take this pressure difference and I'm going to convert that to be in SI units. And here's my semi-empirical parameter. Then I need to know about how is this time constant, this tau. Here's a Bode diagram. You see that the Bode diagram, this shows how well the spool can follow the signal. And again, this is a full signal, which is sine signal. When I'm moving this valve from fully open to fully closed, this is the curve, like 100% opening, 100% closing. And you can see that it is able to follow that very well until the frequency becomes to be roughly, let's say, 35 hertz. This is when it's unable to follow it anymore. That's my time constant. But look this, if not using fully open, but the 5% opening, then it's able to follow the signal further than in the case of fully opening. But let's take the worst possible scenario. So here where the hertz is taken, and this is my time constant. And the final equation is not combined, but the parameters are here. Okay, so let me take myself back here and take a look at the in-class quiz. Okay, so the success rate is going to be 65 today. That's my guess. Okay. So there's you don't see it. Oh, okay. You want to see it? I can tell you. You don't trust me. Not yet. Okay, so you guys ready? So that came with a yes. Okay. Because I think, okay, my guess is 65%. 65, 65, 65, 96, 96. Look at the winner. So where's the winner? Here's the winner. Here's the winner. Very nice. Thank you very much. Thank you very much. So let me see. Okay, so very bad news because we got voting for each of the items. Each of them. And one only is correct. And of course, that's spool position. Yeah, sorry about that. I don't know how is that you made it a week ago. I still don't get it. Like how it is possible. Today you don't score 100%, and the last week there was no proper guidance and you scored 100%. So there must be a technical trick you made for me. Must be. So tell me what is it. I'm not going to be angry to you guys. Really? So how much that makes a difference? Okay. I see. All right. So then, not this. Sorry about that. I need to do it first. This one, and then this one. No, you still don't see it. Ah. Okay, now you see it. Okay, let me tell you something about the digital hydraulics. Okay. So now the digital hydraulics, I wanted to play a YouTube video for you, but obviously my settings are not allowing me to do so. So let me explain it by myself. And then later you will take a look at the YouTube video, which is, I think it was like 3 minutes in a length. So you can easily look at that and really make sense to do so because it's, like I said, that's a big promise to hydraulics. And that, by the way, there is a few institutions in worldwide that are seriously investing to digital hydraulics. And the one is located in Finland. There's one university which is called Tampere University. There's a section which used to be or was a former Tampere University of Technology. And they are investing quite a bit about this digital hydraulics. And they feel that this is going to change their life big time. Really don't know about that, but they're doing serious research in terms of digital hydraulics. All right, so what's the deal with that? Remember, in conventional hydraulics, what you do then is that, so let me take myself back to this slide here. You're moving the spool any position you want. So it can take any position it wants between the fully closed and fully opening. So it can go, in a fraction of the position with no problem whatsoever. And that's called conventional hydraulics. Problem, of course, is that if you look at the pressure here in a supply pressure side, and then in here, which could be close to the cylinder, there could be significant pressure drops. And that's going to be something that is equal than energy losses as well. Now, instead of using this sliding component, you can replace it by using a number of on-off valves. Each of them may have a different size. And these on-off valves can be made in such a way that you can control each of these on-off valves. You can say that you can be only fully open or fully closed, but nowhere between these two extremes, just these two possibilities. Okay, one valve would mean that you can have one kind of a position in your spool. If you put it back to the conventional hydraulics, that would mean one position only. If you have two on-off valves, two in a different size, you have more opportunities. And then you keep on increasing the number of poppet valves, you get more and more possibilities. And eventually, when you have enough of them, then you can hit a lot of possibilities, meaning that the operation becomes to be close to the conventional hydraulics. Here comes the big question. Okay, why you want to torture yourself? Why you want to make your life difficult by using something called digital hydraulics? Because everything was simple and nice, moving spool back and forth, and that was it. And now, instead of that easy life, you want to use a lot of on-off valves, and then, complicated control algorithms to figure out which one of them need to be open and which one of them need to be closed. Okay, the bigger picture is such that you can actually take these digital hydraulics all the way back to the pump. Remember what I mentioned, the pump is a component that makes a decision whether or not you put energy in your system. Now, typically there's a piston pump. Each time the piston pump rotates, you can make a decision whether or not you put the energy in the system or not. Now, if you have a really fast control about the pump and direction valves, you can take the energy directly without significant losses from your pump to your actuator, which is a cylinder or a motor, without significant losses of pressure. That's the beauty behind. But needs a lot of CPU power, needs a lot of clever algorithms to make that happen. But in theory, that's how it works. So digital hydraulics is all about a lot of on-off valves, a lot of poppet valves. And because you have so many of them, you can replace these conventional valves. This is a drawing symbol for a conventional valve. Again, the valve can take any position it wants between fully open and fully closed. And you replace them by different size of on-off valves, and opening and closing them in a proper way, you can get the similar properties. And this is my YouTube video that I would like you to take a look. So please take a look. And this tells you what are the different scenarios. Can I now play this?
In digital hydraulics, the system variables,
Yeah, I
pressure
can
and
play, but
flow,
you don't
are
hear it.
controlled with multiple on-off directional seat valves. Each
No,
valve
no,
is
it's my
solenoid
imagination.
operated
So,
and has
what is
only
it?
two
No,
possible positions,
no.
on and
Okay,
off.
take a look at
This
this.
is why the
So
term
this tells you what
digital
are the
is
different
used. These
possibilities
valves
regarding
are
the
used
motion.
to
Now,
implement
if you
all
have
valve functions,
16 on-off
such as
valves,
pressure,
you
flow,
can
and
get
directional
65,000
control.
different
Contrary to a traditional
scenarios.
hydraulic system, which has many
That's how
different
it works.
types of
You
valves,
know, they
a
claim,
digital
this
hydraulic
is not
system
my
has a
statement,
large
but they
number of
claim
only on-off valves. By
the people that
connecting
are
in parallel
developing these
three
digital
on-off
hydraulics, they make a
valves of different
claimant
sizes,
that
such as
there is a
1,
zero
2,
leakage,
and
less
4,
power losses.
7
This is
different flow
significant.
quantities can be
It
achieved.
really is to
5
do
on-off
so.
valves can
That's a
achieve the
big deal.
control resolution of a traditional
Accurate
proportional
control.
valve. A
Yeah,
group of on-off
maybe
valves
that
in
too.
parallel make
But
up a digital flow
complicated
control unit,
algorithms
called
because so many
DFCU.
different
At
scenarios.
least 4 of these units are needed to substitute a
So
proportional
that's
valve in a
digital
hydraulic
hydraulics.
circuit. Each DFCU
Oh,
is used
all
to
the
control
participants,
one of the 4
they
control
hear
edges.
this,
The main benefit of digital
but
hydraulics
you
is
don't.
the ability to control each control edge independently. This reduces power loss and
I don't know
enables
if I should be
precise
quiet or
control.
not.
Additionally, seat valves
You
have
guys take a
zero
look at this later.
leakage,
But unlike
as opposed
participants,
to the
they
high
see
leakage of
they hear that
proportional
already.
valves. However,
Now
the
they're
challenge with
angry
digital
because I keep on
hydraulics is the
talking.
complexity of the control
Okay, my last
algorithm.
in class quiz.
Each valve needs to be controlled
Am I?
individually, and this
No, okay,
results in
this is.
large numbers of valve position combinations, although each valve has only 2 possible positions.
I'm done. No, but hold on, hold on. Digital direction valve consists of spool controlled by a computer, none of a number of on-off valves, spool controlled by a magnet, spool that moves incrementally. Manual is correct. Okay, let me take myself back to the Socrates. Just a second. And this, by the way, would be call it for the day. Next. Okay. Okay, now there is a video in the background. Sorry, sorry, sorry. I think it is done. Okay, now everything is okay. Back here. So, digital direction valve consists of spool controlled by a computer. Spool. Now, here's the keyword spool. Number of on-off valves. Spool controlled by a magnet. Spool that moves incrementally. Okay, how many answers we collect the last time? 60, 67. Okay, and this is it. So that's last slide of the day. So we continue to discuss about the different components a week from now. And you can go because if we're gonna score 100%, I will let you know. You can trust me. Oh, you don't trust me? Yeah, it's not gonna be 100 this time. You're absolutely right about that. But can you see the? No, that's not on. Okay, so we got 50, 61, 62, 64. Again, the last time we got 65. Was it 65? So okay, and the game is on. Oh, by the way, last time I think we got the winner about the game, this success rate guessing game. Okay. And success rate today is 71, 86, 71. Okay, so good news is that you guys are back to the normal. So I don't need to be worried about you guys anymore. I was very worried about what's going on because, if you start scoring 100% all the time, I need to ask some medical attention to you guys. So, but we're back to the usual. So that's a good news. Another piece of good news is this: no more dancing. Okay. Hey, thank you very much, guys, and see you in next week, Monday. So 2 or 3 more weeks to go. So we're getting close to the end. So you're almost off the hook. Almost. Okay. Thank you, guys.